Good morning, AP Chemistry people. This is a good day. This is nitrogen triiodide day. We're gonna have some fun today. So we've got some thermo data up here. Nitrogen triiodide, right? Reacts to turn into nitrogen and 3 iodides. So I looked up some of the data. Some of it was much more difficult to find. I actually had to bust out the old CRC that you might remember from earlier this year, because some of the data I couldn't even find it online anywhere. I was looking for the entropy of nitrogen triiodide and was unable to find that. So anyway, if we look at this from a delta H point of view, right, that's going to be products minus reactants. So my products so for my delta H of reaction, it's going to be products minus reactants. So that's 0. 0 times 3 plus 0, so 0, minus my reactants, which is negative 143 times 2. Wait a minute, that's going to be a positive. Did I flip my sign on that on accident? Because it should be a negative. So this must be a positive. Yeah, because it's that products minus reactants. Yeah, so this was a positive, not a negative on that. So we do 143 times 2, and that gives us 286. So our delta H of reaction is a negative 286 kilojoules per mole. Nothing about that tells us anything all that exciting. It just tells us this is an exothermic reaction, right? Our entropy, right, would be point delta S is going to be 0.192 plus 116 times 3. So that's going to be our S of our products plus 116 times 3. And that's going to give us 540, because that's a 0.116 there. And then if we subtract our reactants, that's going to be 0.094 times 2. So 0.094 times 2 gives us 188 joules per mole Kelvin. And so if we do 0.540 minus 0.188, that gives us a delta S of 0.352 kilojoules per mole. All right, so if we want to know our delta G of our whole reaction, we can do our delta G of our whole reaction. We just need to do delta H minus T times delta S, right? So negative 286 minus, we're going to do this at room temperature, which we'll say is 298. It is freezing cold in here as always, so it is not 298, but we'll pretend it is, times 0.352. So it is becoming more disordered. So entropy is favoring this happening. Enthalpy is favoring this happen. So this is absolutely a spontaneous reaction. So overall, that gives us a delta G of negative 390 kilojoules. Now that's for reaction, not per mole. You divide it by 2 to get the per mole, because these that I was listing was delta H's of reaction and that kind of stuff. So it releases heat energy, it releases randomness energy, and it is a negative delta G. It is spontaneous. What makes this fun, though, isn't just the thermo, right? The thermo is exothermic, right? It's going to drop down, but it has a tiny, tiny, tiny little activation energy. That's supposed to go up, but only a tiny, tiny, tiny amount, right? So it's called a contact explosive. So why would this be a contact explosive? Why would it be such an easy thing to make react? Nitrogen triiodide, right? You hear nitrogen, we're thinking, well, a lot of explosive things have nitrogen, like nitroglycerin is a contact explosive, but you have to smack it with a hammer. You have to hit it pretty hard. This sets off easier than that. And really it has to do with size stuff. So nitrogen is a tiny little molecule. We think periodic table, right? It's on the second energy level. It's over to the side a good bit. So it's a pretty small central atom. And then you've got 3 iodines, and iodines are pretty big atoms. So if I try and stick 3 iodines on here, I'm going to use these pink balloons that were some p orbitals and stuff earlier. And it's got that lone pair of electrons, so they're all forced onto the same side. Hey, come back here. They're all forced. Stop falling away from me. They're all forced onto the same side here. And so if you can imagine my balloons here, right? I've got my nitrogen in the middle, and then I've got these 3 balloons that are all trying to force their way at 109-degree bond angles here on the bottom side. There's just a lot of steric strain, right? There's a lot of bond strength, strain because the iodines are pushing away from each other. Having a tiny central atom and a bunch of really big outside atoms makes things difficult on this whole thing. So it's easy for it to fall apart and break apart, right? So we're going to do that and a couple of times. I've set this up 3 days in a row, and the other 2 days I kind of went big. I was like, well, there's no students here, so I can go a little bigger. And they kept self-igniting. So you make it wet, and when it dries, it's then a contact explosive. And so I made it. And then I have to let it dry. Well, when it dries, sometimes as they dry, they shift a little bit, and they'll just self pop. And so I made some bigger ones, and they did not work. So, well, they did work. They worked on their own. So I made some little bit smaller ones, but we'll give those a try here in just a second. So that's what it looks like. It's that brown stuff there in the middle of the filter paper. We've got 3 of them, so hopefully at least we can get 1 or 2 of them to pop pretty nicely for us. So I'm going to set you there. Got a little meter stick with a feather on it, and we'll give it a try.